Hi, I'm Airman Roger Wood. I'd like to spend a while with you talking about antennas. Some of the points we'll be discussing in this lesson are what's an antenna, some different types of antennas, the physical and electrical characteristics of antennas. We will compare the half-wave and quarter-wave antenna and learn the difference between the induction and the radiation field. Well, first of all is an antenna. An antenna is any structure or device used to detect or radiate electromagnetic waves. Well, as you can see, this is pretty general. We can't just grab a handful of wires and say, okay, I'm ready, let's radiate. We must get more explicit. For instance, the same antenna you use in your house radio would hardly be sufficient for an airborne radar set. The big 300-foot parabolic antenna used in ground radar would look rather silly in your kitchen, too. Military radios and radar handle a variety of purposes, so they require a variety of antennas. If we are to pick the right antenna for the right job, we must obviously know more about them. By the time this series of lessons dealing with antennas is over, you should be familiar enough with the subject to know which antenna to pick for which job. Let's take a look at some different types of antennas. This is a model of a complete GCA set. It includes the radar antenna and the radio antennas. This is a model of a radar set used in ground radar. And this is a model of an antenna that might be used by a commercial radio broadcast station. Of course, the real thing would be much larger. In fact, even you and I are antennas. No matter where you may be, in a building or in the middle of a desert, there is always electromagnetic energy in the air around you. And your body is acting as a receiver antenna to pick it up. Here, I'll show you. Someone please throw me some RF energy. Thank you. Now I'll feed this energy from my hand into this oscilloscope, and you can see it on the face of the scope. Well, naturally, you know you cannot catch RF energy in your hand. The RF waves are striking my body all the time, and by touching the input terminal of the scope, I merely transfer them from my body to the scope. I couldn't feel the electromagnetic waves in my hand any more than you can feel the RF waves that are striking your body right now. You can't see them, you can't smell them, you can't hear them, and you can't feel them. So how do we know they're there at all? Well, if they aren't there, the world of electronics is in a lot of trouble. Actually, physicists and mathematicians have only derived theories about the radiation of electromagnetic energy, and all the advances made in the field are based upon these theories. Now, before we get too far into the subject, there's one point we should realize. You know that the purpose of any antenna is to transmit or receive RF energy. What you may not know is that most antennas will do both. That is, all the antennas we'll be studying will radiate energy as well as receive it. This is called antenna reciprocity. Antenna reciprocity. Now let's fill in item number 2 in the TVI guide. The ability of an antenna to both send and receive electromagnetic energy is called antenna reciprocity. Antenna reciprocity. Now let's for a moment consider the physical characteristics of an antenna. An antenna is constructed of any metallic conductor. It could be wire or a rod or metal tubing or any material that will conduct the flow of current. As we study the many different types of antennas, we'll see how each is constructed. Now, the electrical characteristics of antennas are quite another matter. For a starter, let's digress a little bit to the transmission line. You'll recall the open-end quarter-wave transmission line contained standing waves of current and voltage. at the termination of the line, current was minimum, voltage was maximum. Also, we have a very small external electrostatic field because current is flowing in opposite directions, and the field will tend to cancel itself out. Let's say this is a piece of open-end transmission line 1/4 wavelength long. If we were to split the conductors apart and put them end to end, current will be flowing in the same direction in both conductors. Now the electrostatic field is released into the space around the conductors and expanded because the currents are aiding the field expansion. We now have what is known as a basic half-wave dipole or Hertz antenna, or sometimes called a doublet antenna. As you can see, the current and voltage wave shapes are changed somewhat. They are still in the same direction in polarity as they were before we split the line. But now, the current is maximum in the middle of the line and minimum at both ends. The voltage is represented as being positive on this side, negative on this side. Naturally, resistance varies inversely as current, so it will be maximum at both ends and minimum in the middle. It is an established fact that the impedance at the center of a simple dipole antenna is about 73 ohms. Now, this is not an impedance you can measure with an ohm meter, however. This is the impedance seen by the power source and is composed of two resistances. First, regardless of how good a conductor is used to make the antenna, there will always be some heat loss as current flows through it. In most antennas, the heat loss is held to a minimum so that the efficiency is about 90%. Let's refer to the TVI guide, item number 4. At the center of a dipole antenna, current is maximum. Voltage is minimum, and impedance is minimum. At the center of a dipole antenna, current is maximum, voltage is minimum, and impedance is minimum. Now, the other resistance we mentioned is known as radiation resistance. This is the loss of energy due to its propagation into space. Some of the energy is taken back into the antenna when the induction field collapses. The rest is radiated out into space. This is known as the radiation field. This is covered under item number 5 in the TVI guide. The two fields of RF energy surrounding an antenna are the induction field and the radiation field. The two fields of RF energy surrounding an antenna are the induction field and the radiation field. Well, now that we have formed the basic antenna, let's see what it looks like electrically to the power source. Well, since it is actually a split open-end quarter-wave transmission line, it will exhibit the same electrical properties. In other words, it will appear to the power source as a series LCR circuit. Now, if the antenna is cut to serve one frequency, it will be physically and electrically 1/2 wavelength for that frequency. However, if it is to serve a variety of frequencies, it must be varied in electrical length to be 1/2 wavelength for all those frequencies. Let's say an antenna cut for a particular frequency is fed a higher frequency. Well, we know that a series resonance circuit above resonance acts inductive. So the antenna at this higher frequency will appear to be longer than 1/2 wavelength. In order for the antenna to give us maximum radiation, it must appear as a resonant circuit, or completely resistive to the power source. Since it now appears as an inductive load, we can make it resonant once again by adding a capacitance in series with it. Conversely, if the antenna were cut for a particular frequency and fed a lower frequency, it would appear shorter than 1/2 wavelength, or as a capacitive load. And we would correct for this situation by adding an inductance in series with it. In other words, we can alter the electrical length of an antenna by adding an inductance in series with it to lengthen it, or by adding a capacitance in series with it to shorten it. Now let's go back to the TVI guide, item number 6. It is possible to electrically lengthen an antenna by adding an inductance in series with it, and shorten it by adding a capacitance in series with it. It is possible to electrically lengthen an antenna by adding an inductance in series with it, and shorten it by adding a capacitance in series with it. Now, we said that as current flows in a conductor, it sets up an electrostatic field around the conductors. The lines of force, which we call E lines, are flowing in this drawing from the positive end of the conductor to the negative end. Naturally, we can only show you the two-dimensional view of the field, but we can see that the lines of force would surround the antenna completely. Now, you know from your study of coils and transformers that when current is passed through a wire, it also sets up a magnetic field around the wire. Well, the same is true when current is passed through the antenna wire. This can be represented graphically this way. Here, too, there are lines of force covering the entire length of the antenna, but we've drawn only a few for simplicity of explanation. These lines of force are called H lines. These lines would change direction as the direction of current flow changed. This combination of the two fields, electrostatic and magnetic, or E lines and H lines, make up what is known as the induction field around the antenna. It expands and collapses with a change in the direction of current flow. The strength of the induction field varies inversely as the square of the distance from the antenna. That is, the further away from the antenna, the weaker the induction field. Now let's fill in TVI guide item number 7. The field of energy that collapses back into the antenna is the induction field. The field of energy that collapses back into the antenna is the induction field. Now, in the study of transformers, you learned that there was always some of the magnetic field that was not transferred from the primary to the secondary, but was lost in space. We called it flux leakage, and in most cases it was a disadvantage, because we wanted as much energy as possible transferred across the transformer. In the case of antennas, it is just the opposite. We want to lose as much of the magnetic field as possible into space. In this case, it is called radiation. The portion of the magnetic field that does not collapse back into the antenna, and the portion of the electrostatic field that does not collapse back into the antenna, comprise the radiation field. The strength of the radiation field varies inversely as the distance from the antenna. That is, the further away from the antenna, the weaker the radiation field. This subject is covered under item number 8 in the TVI guide. The field that is radiated into space is the radiation field. The field that is radiated into space is the radiation field. Now, before we go any further, let's review some of the things we've just covered. First, there are many different types of antennas, but no matter what the purpose of an antenna is, it must be constructed of a material that will conduct the flow of current. Secondly, the ability of an antenna to transmit and receive is called antenna reciprocity. Then on the half-wave dipole, or Hertz antenna, we looked at the standing waves and saw that current was maximum in the center, minimum at each end. Voltage is maximum at each end and minimum in the center. And the impedance, which is made up of the heat resistance and the radiation resistance, is about 73 ohms in the center of the dipole to several hundred ohms at each end. The antenna we are currently discussing appears to the power source as a series LCR circuit. We can change the electrical length of an antenna by adding an inductance in series with it to lengthen it, or by adding a capacitance in series with it to shorten it. We just now discussed the fields that are set up around the antenna by the flow of current in the radiating element. The lines of force in the electrostatic field are called E lines, and the lines of force in the magnetic field are called H lines. Together, the two fields comprise the induction field around the antenna. Now, we just discussed the induction field, and a moment ago we mentioned the radiation field. Just what is the difference? Well, the induction field is the field immediately surrounding the antenna, which is taken back into the antenna when the field collapses. The radiation field is the field that is not taken back into the antenna, but is radiated out into space. Let's graphically take one complete cycle of AC current through the antenna and see how the two fields are developed. We'll start at a point of minimum current and assume that a magnetic field has already been built up. Now, as the current flow increases, the magnetic field starts to collapse. The electrostatic field is built up here at point B. As you can see, the electrostatic field is developed 90 degrees after the magnetic field. Now, still at point B, the current starts to flow in the opposite direction. The electrostatic field starts to collapse, and the magnetic field is of maximum intensity again at point C. Current flow is again 0. This cycle repeats itself during the positive alternation of current flow. From this, you can see that the electrostatic and magnetic fields are developed 90 degrees out of phase with each other. Now let's take a look at the two fields one at a time and see how they are radiated out into space. First, the electrostatic field, or E lines. In this simplified drawing, you can see two sets of E lines extending from the positive end of the conducting element to the negative end. At this point, the voltage is maximum, and the field has maximum intensity. You will notice that the center of the lines is pushed out away from the antenna. This is because lines of force traveling in the same direction repel each other. Now, as the voltage drops, the field starts to collapse, with the 2 points of opposite polarity moving toward the center of the antenna. Notice that the centers of the lines are still held out away from the antenna. As the voltage approaches 0, some of the lines of force will collapse back into the antenna, but the ones farthest away come together and form a complete loop. Notice the direction of these lines of force next to the antenna. At this point, the voltage is again 0. Now, as the current reverses and the field starts to build up in the opposite direction, lines of force are built up around the antenna in the opposite direction, as before. These lines of force, traveling in the same direction as the lines of force in the closed loop, will repel these lines of force in the closed loop and force them out into space. This process repeats itself as long as alternating current is fed into the antenna, so the E lines will continue to be pushed out into space. However, an electrostatic field by itself cannot sustain itself in free space. It must be supported or aided by the magnetic lines of force. In other words, in space, E lines produce H lines, and H lines produce E lines. Let's see how the H lines are radiated. The mechanics are the same as for the electrostatic field. Some of the magnetic lines will collapse back into the dipole, and some will be repelled into space when the current reverses and the fields build up in the other direction. Notice that this field, too, is of maximum intensity at the center of the radiating element. Now we have both E and H lines literally snapped off the dipole and free in space. What happens to them now? Well, a mathematician named Maxwell derived two very important equations upon which the entire theory of radiation in free space is based. He said that electrostatic lines of force in space produce magnetic lines of force, and magnetic lines of force in space produce electrostatic lines of force. Or in layman's language, the E lines exist because of the H lines exist because of the E lines. As they radiate into free space, they support each other. Let's take a look at this model. As we said earlier, the H lines are closed loops around the antenna itself. And the E lines are closed loops at 90-degree angles to the H lines. You can see the mock-up is built so that where the E and H lines connect, they are at 90-degree angles to each other. Now, if we took one cross-section of both fields at some point in space and expanded it, it would look like this. The vertical lines are the E lines, and the horizontal lines are the H lines. This cross-section of an electromagnetic field is known as a wave front. We've seen how the lines of force leave the antenna. This is the position they would be in when they strike the receiving antenna. And for each half alternation of the current in the transmitting antenna, we would have another wave front. Our next subject is polarization. When an antenna is installed vertically and the E lines move over the ground vertically, it is said to be vertically polarized. When it is installed horizontally and the E lines move over the ground horizontally, it is said to be, of course, horizontally polarized. This subject is covered in the TVI guide under item number 11. E lines traveling vertically to the ground means that the antenna is vertically polarized. And E lines traveling horizontally to the ground means that the antenna is horizontally polarized. Now here is a model of the radiation pattern of a vertically polarized half-wave dipole antenna. It rather resembles a donut, doesn't it? As you can see, the point of maximum radiation is at a 90-degree angle to the antenna, the point at which we had maximum field intensity of the E lines and the H lines. There is no radiation from the ends of the antenna. These are the E lines, and these the H lines. A moment ago, we showed you a wave front. If we were to take a close look at this section of the radiation pattern, right here, that would be a wave front. Notice that the dipole radiates in all directions. This is an omnidirectional pattern. Radiating in all directions means omnidirectional. Just like when you drop a pebble in water, the waves radiate in all directions. This is omnidirectional radiation. Now, so far in this lesson, we have talked about the half-wave antenna, or an antenna that is electrically 1/2 wavelength long. I know you're familiar with the formula. Frequency equals 3 million over wavelength. When the frequency is in megacycles, wavelength will be in meters. Well, you can see from the formula that as frequency decreases, wavelength increases. When we get down into the lower frequency ranges, 1/2 wavelength would be quite a long antenna. We need an antenna that will do the same job that the half wavelength antenna will do, but will be shorter. Marconi is responsible for deriving a method that makes this possible. He used a quarter wave antenna. Naturally, this would be half as long as the half wavelength, but will it do the same job? Let's say we want to use the antenna for a commercial radio broadcast station. Well, when a radio station is broadcasting on frequencies between 550 and 1600 kilocycles, a half-wave antenna would be quite large. A quarter wave would be better. Well, Marconi found that if you cut a half-wave antenna in half and ground one end of it, it acts the same as the half-wave antenna, even though it's only a quarter wavelength long. According to his theory, the quarter wavelength radiating element will radiate the energy, and the ground will act as the other half of the antenna, so it will retain its half-wave characteristics. And his theory must work because commercial radio broadcast stations all over the world are using grounded quarter-wave antennas to broadcast their programs. Here's what actually happens when you cut the half-wave antenna in half and ground one end of it. This is the radiating element. This, of course, is the ground. And this is what is known as the image. If we had X-ray vision and could see the current and voltage wave shapes below the ground, the entire pattern would look exactly like the half-wave dipole or Hertz antenna. Since Marconi's theory was responsible for the development of this quarter wave antenna, it is called the Marconi antenna. Let's now complete the final item in the TVI guide, item number 13. The grounded quarter wave antenna has the electrical characteristics of the half wave antenna because the ground acts as an image for the other half of the antenna. The ground acts as an image for the other half of the antenna. Now let's take the mock-up of our radiation pattern for the half-wave antenna and compare it to the pattern of the quarter-wave antenna. And here it is. Looks like a half a donut, doesn't it? Well, this would be the radiation pattern for any commercial radio broadcast station under perfect geographical conditions. This would be the ground, this the antenna, and this the invisible radiation pattern, actually measuring several miles across. Actually, the only time it would be a perfect pattern is when there are no hills or trees or houses or any obstructions to deflect the radiation pattern. Perhaps in the middle of the Sahara Desert, the pattern would resemble this. But who's going to build a radio station out there? Before we close, you'll notice that your TVI guide contains some drawings. They are there for your future use and review of the subject. Now let's hit the high points again to be sure you have everything. The first thing we had to realize in the study of antennas is that they must perform many different jobs, so we must have many different types. The two types we were primarily concerned with in this lesson were the half-wave dipole, or Hertz antenna, and the quarter-wave, or Marconi antenna. we saw that the same antenna can transmit and receive, and this ability of an antenna is called antenna reciprocity. The half-wave dipole antenna appears to the power source as a series LCR circuit. We can change the electrical length of an antenna by adding capacitance or inductance in series with it. The center impedance of a dipole is about 73 ohms and is composed of a heat resistance and what we call radiation resistance, or the energy actually lost into space. The electrostatic and magnetic fields that collapse back into the antenna comprise the induction field, and the lines of force that are snapped off the antenna and forced out into space make up the radiation field. We saw how the two fields, the E and H field, are produced 90 degrees out of phase with each other, how they are snapped off the antenna, and how they support each other in free space. Most commercial radio stations use the grounded quarter-wave antenna for broadcasting. A grounded quarter wave uses the ground to produce its image, so it has all the properties of the half-wave dipole. Now, we said that because of geographical conditions, a perfect radiation pattern was almost impossible to achieve. In a few minutes, we'll be back to tell you how the Earth and the sky and reflecting objects alter the radiation pattern.